Okay. So, we begin this course which is given the name Discrete Time Signal Processing. When you say discrete time, it means there is a signal. Normally, we come across analog signals. Analog signals are actually waveforms of time. In general, time it could be space also, like if it is an image, continuous image, it is a function of two x's, x and y, it is a continuous function, that is an analog image. Similarly, an analog waveform as a function of time could be like this, they are analog waveform. You can call it x subscript a for analog as a function of time. Okay. So, as a function of time, t is a continuous variable, time t, and you plot it is called an analog signal. It can come from say somebody's speech, like I am saying something. If you record the waveform as a function of time, it will be like this. It can come from any source, from communication source, from from various sources. You just convert it into a waveform function of time. So, for us signal means, analog signal means something which is a function of time or function of one variable, either normally we deal with functions of time, or in the case of images function of space, but they are at least function of two variables, x axis, y axis, something like f x comma y. X is continuous in x axis, y is continuous. At each x y there is a value, pixel value, I mean intensity value, and since x and y are continuous, there will be a continuous image. That is a two-dimensional signal. One-dimensional signals are typically function of time. Okay, analog function. This is analog. But if I discretize the time, that is, I will not observe it at all points, I will observe it at uniformly separated points, maybe 0, then t, then 2t, but capital T is called the period, sampling period, that I am taking a sample here, next sample here, next sample here, next sample here, dot, 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 dot. So, these sample values, when I consider the sample values, this axis is no longer time. We in fact throw away the notion of time from here. We only bothered about index. This is a 0th sample. So, this is n equal to 0. This is the first sample, n equal to 1. So, this gap has nothing to do with capital T. You can make it very narrow, very wide. It means nothing. It is only 0, 1, 2, 3. What matters is which is first sample, which is second sample, which is third sample. There is 0th sample, first sample, second sample, third sample, like that. So, that means this axis is discrete, and that is why it is discrete time. That is, if the original signal came from a function of continuous time, then if you discretize the axis, you just get points 0, 1, 2, 3, okay, and corresponding sample values you plot, you get a sequence. This sequence is a discrete time sequence. Okay, we just call it a sequence, and I repeat again, there is no notion of time here. This n has got no time, it is just an integer, dimensionless, unitless. Just n equal to 0, n equal to 1, n equal to 2, n equal to 3. So, who is 0th, who is first, who is before whom, who is after whom, these are the things matters. And then I will call it x n. This will be a sequence, we will also call it discrete time signal. Now, the advantage of this thing is, this representation is that if we throw away the notion of time, you can take care of any sequence of numbers, because maybe a sequence is obtained just manually, not necessarily by sampling an analog signal. A sequence of numbers, them also I can process here, like 0, I mean if you get a sequence of numbers say 1, 2, 9, 5, minus 7, dot, 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 you automatically generate, or maybe a computer is generating sequence of numbers. I just plot them one after another, 0th, first, second, I put a 0 value, I set one origin, index origin for one of them 0, and then 1, 2, 3, and put them accordingly. Okay. So, what I get is a sequence. So, not this, but this time it is not obtained by sampling any analog signal. So, this is more general. If I throw away the notion of time, just bring in index n and call it 0 or 1 or 2 or 3, I can take care of not only sequences obtained by sampling an analog signal, but any sequence, manually generated, sequence of numbers, sequence generated by computer, okay, data generated by computer, all. That is why here after discretizing, we do not write in terms of time, we just write in terms of this. Now, the question is, why should I, suppose I am considering only this analog signal and a sequence obtained by sampling this like this as I discussed. Suppose now, why should we go for this discrete time signal processing, that is processing this rather than the analog waveform? Answer is, analog waveform processing means, actually what is processing? Processing means I should be able to do various operations, as many operations as possible on that input signal. Now, suppose this is an analog signal, I want to multiply, I want to divide by some number, some fraction. This is possible in analog domain. Just take a resistive divider R1, R2, okay, set the values of R1, R2 so that you get a fraction of it. That is very easily doable. If you want to multiply by a number, the signal, if my processing involves multiplying by a number greater than 1, that means amplification. That is also very easy. You pass it through a common emitter amplifier or common base amplifier or op-amp amplifier, whatever, adjust the gain. So, you can do this amplification. Okay. So, this operation where you have to multiply this by a number greater than 1, in analog domain we can do that, no problem, using amplifiers. Then suppose you want to add two such waveforms, okay, x1, x2, two such waveforms you want to add. That is also possible, because what you do there, you use an op-amp based adder, okay, and just give the two signals, you get an output. If it is inverted in sign, you pass it through another inverting amplifier and all that. So, adder is very much there. So, I can add, I can carry out addition operation, and thereby I can carry out subtraction operation also, not a problem. Multiplying two signals in analog domain, that is also possible. There are multipliers, analog multipliers which can take two signals, 4 quadrant multipliers, and get you output. Can I take log of a signal, that every value of this waveform, I take the log of it? Can I do a logarithmic calculation? Yes, there is something called log amplifier using op-amp. So, you can carry out log, you can carry out anti-log. So, all these operations and some more operations are possible, but point is number of such operations is very limited. You cannot go beyond a few. For instance, if you have to take say 10th root of this, or even square root, cube root, can I do that? Not easily. Any other operation, if I take this value, if I have to carry out trigonometric operation, so every value I have to take it sine or cos, how much? This is very difficult. In analog domain you cannot do, but if I convert them into a sequence, so just sequence of pure numbers and give these numbers to a computer, then in a computer I can run an algorithm on them, on the sequence, and in my algorithm, through this algorithm I can do any kind of operation, all operations are possible. So, that is digital processing, processing these sample values, but moment I make them available in this form and give it to a computer, computer can work only on numbers, discrete elements, computer cannot work on continuous elements. So, discrete numbers one after another, so my algorithm will work on them and give you any operation you want. So, the range of operation becomes immense. Anything is possible if you go for digital processing. But only thing is, you can ask me a question that look, here I am not taking the entire waveform, okay, I am not taking the entire plot, I am only taking some values, one value, another value, another value, another value. I am leaving out this intermediate waveform part, intermediate values. Then am I not losing something? Am I losing some important information because I was crazy to get into some kind of digital processing? Answer is no. This is the beauty of digital signal processing, that if suppose this analog function has got a finite bandwidth, then it can be shown, this is a fundamental theorem in DSP, that if I take the samples close enough, that is make the sampling period less than equal to some value, or sampling frequency greater than equal to some value, okay, then the samples are good enough to carry all the information of the envelope, even if the intermediate part is missing. That limit gives us to actually what is called Nyquist sampling rate, which I will cover later. That is, there is a fundamental limit for band limited signals, that limit is called Nyquist rate. If you sample this analog signal at a frequency higher than Nyquist frequency, that means sampling period is shorter than that, more dense, more close, then those samples carry all the information of the analog envelope, you do not lose anything. That is fundamental. That gives you a permit, a license to replace this analog waveform by a series of discrete samples, and which can be easily processed by a computer or by a dedicated digital hardware, and any operation can be done. As you understand, in digital processing, number of operations can goes to infinity. You can do in fact anything you want, because you will be basically implementing an algorithm. Okay. Algorithm means like write algorithms in computer where you can do anything. So, same thing you can work on that, but algorithm can never work on continuous stuff. That is why discrete has the big advantage. This is the main motivation for going into discrete time signal processing, or rather digital signal processing, discrete time signal processing, right. Now, there is one more reason why we go for this, but before that I am coming to another point. You will be coming across two phrases. One is discrete time signal processing and sometimes digital signal processing. Question is, are these two same? Actually, here in this waveform, this axis is discrete 0, 1, 2, 3, but this amplitude axis, y axis, it is not discrete. The sample can take any value. But when you give it to computer, every sample we pass it through a quantizer, this analog to digital converter, and then quantize it to as a 16-bit, or that will give a 16-bit output, or ADC I mean, or 24-bit output, or 12-bit output, or 32-bit output. So, basically this can take some quantized values only. So, that time this axis also get discretized. That is, if the y axis is this, anything falling in this range, maybe quantized to will be taken to be 0 value. Anything falling in this range may be taken to this value. Anything falling in this range may be taken to this value. Okay, and then they are represented by number of some binary word. So, that is quantization. You are familiar with the ADC and all quantization. So, that time y axis is also discrete. So, the samples actually take discrete values. So, in pure digital processing, these axes also discretized, because they take discrete values. Okay, because after all they are dependent by fixed numbers, say 8-bit numbers, so 2 to the power 8, 64 possibilities only. So, 64 labels will assign. Okay, around the label there will be a band, anything falling within the band will be equated to that label. Then another label, around that there is a band, anything falling within this band will be equated to this label, so on and so forth. Okay, that is why this axis is also discretized. This will be a pure digital signal, where both x axis, that is this axis of n, and the y axis, they are discretized. But the problem is, if you really start using y axis to be discretized also, x axis to be discretized also, then analysis, other things become very difficult. That is why we assume that number of bits after quantization, number of bits is very large. So, therefore, these bands are very narrow. Okay, and the levels are very close to each other, and bands, instead of being two levels being here, they can be very close to each other, almost adjacent to each other, and therefore, they are almost like continuous. That is, if you assume that number of bits is large, the gap between two levels, discrete level will be very small. So, you can assume the y axis to be almost continuous, and then this becomes just a discrete time signal, continuous amplitude, but discrete time signal. We make this assumption in doing all analysis and design and other things, because if you want to carry both the discrete in time, discrete in amplitude, then it becomes difficult. But then again the question comes that I am making an assumption, so there is an approximation, after all y axis is also discretized, but I am making it, I am assuming it to be continuous under the assumption number of bit is large. But am I not introducing any error? Answer is yes. So, after making this assumption that y axis is continuous, and then going ahead with my design and other things, then we then take a look and try to estimate how much error in my design has gone in because of this assumption that y axis actually is discrete, but I have assumed to be continuous, okay, because the levels are very close to each other. So, that analysis is called finite precision analysis, or finite word length analysis, and we estimate, okay, because of this approximation how much error went in. Okay. So, again by that we estimate whether that error that went in is okay or not. but before that till design level we assumed it to be continuous. So, this is the approach. When you go for design, analysis, everything, take the y axis to be continuous, x axis to be discrete, it becomes a discrete time only signal, discrete time signal. Then after doing your circuit, after getting your design and all that, then carry out some further error analysis where you try to find out the effect of this approximation on the y axis, that y axis actually is discrete, but you assume to be continuous. So, what kind of error, how much error does it give rise to? Okay, how to keep that error within limit, within bound, make it small and all that. That is a separate chapter, that is called finite word length analysis. So, this is the difference between discrete time signal and digital signal. Now, there is one more reason why this digital signal processing or equivalently discrete time signal processing here became very popular. One is of course in the digital domain you can do any processing. Another is last 30 years or so we have seen tremendous growth in digital VLSI, not so much in analog VLSI, but digital VLSI. Okay. And that is why emphasis shifted from processing in analog domain to digital domain, because in digital domain you can do millions of operations, so many gates and others can be packed in a small IC and a chip can be made. So much of operation can be put in one IC. Okay. So, that is why emphasis shifted to this. Okay. These are the two main motivations. I suggest some books also, though I tell you that be careful, always follow my lectures, because I normally do not follow any book. I teach from my understanding, and here and there you will always find some new concepts which are not given in any book. Okay. So, that should be a value addition. You should be careful, you should take note of this. So, the books are this. By Alan Oppenheim and Ron Schaefer. I do not remember the publisher, it may be Prentice Hall. But these two authors, way back in mid 70s when the DSP topic just came up, they wrote a fantastic book that is just digital signal processing. I believe Oppenheim, Schaefer, and there is another third author that I do not remember, but this is a famous book. But I personally like this book by the same authors. This is a fantastic book, much shorter, much thinner than that, but that is a fantastic book. This is more elaborate and sometimes unnecessarily elaborate, unnecessarily lengthy, in my opinion, of course. Then there is a book, DSP, I do not remember the exact title. By Proekis, John Proekis and Manolakis, full name I do not remember, his title is Manolakis. It is a Prentice Hall book, a very good book. Then there is a DSP book by S.K. Mitra. This is also very good. These 4 books I am listing, they are pretty good, they are very good, having very good examples and everything, but please follow my lectures, because my lectures, for my lectures I do not follow any of them. I teach from my own understanding, and here and there I give inputs which are not easily found in books, and you have to be careful for that. So, with this background, I start this course now. So, our starting point, as I told you, is a sequence of numbers. So, this axis is n, there is no concept of time here, just computer, for processing we take only the numbers, even if the analog signal is quantized, even if we started by sampling an analog signal, we take every sample by analog to digital converter, then digitize the sample, see the sample height, that is the number, we process the numbers. Okay, this sample so much value, next sample, so much value, next sample, those values, those numbers, numerical values, one after another. So, it is a sequence of numerical values, these values only I process. That is, one sample value so much, another sample value so much, another so much, another so much, another so much, another, only the values I process, sequence, not. So, this time of separation between these two samples is not my constant here. Okay. Another reason is that whatever algorithm I want to propose out of them, that should be independent of the sampling period. That is why we only take the numbers, the sample heights, and they one after another they come and they form a sequence. We denote it by say x n, h n, y n, v n. So, this is my x 0 at 0th point, this is my x 1, this is my x 2, this is my x 3 and dot dot dot. I can have on this side also, this is my x minus 1, this is my x minus 2 because this is 0, this is 1, this is 2, this is minus 1, minus 2 dot dot dot. This is a typical sequence of numbers. It could have come by sampling an analog signal. So, and then I just take the sample values, the train of samples one after another. I do not care for the time of separation, just the sequence, who is after whom, who is before whom, who is 0th, who is first, who is second, like that. Or this could be generated just as a sequence of numbers manually by myself or by a computer which is generating data and things like that. Okay. So, this is a sequence. Sequences, there are some properties. First, if I give you one sequence x 1 n, something like this, dot dot dot, and x 2 n x 2 n dot 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 dot. When I add x 1 n plus x 2 n, by this I mean another sequence y n, where y n will be like this: 0th sample, so this is the 0th sample and 0th sample, these two will be added. So, new 0th sample, sorry, this is 0th sample and this is 0th sample, these two will be added, new 0th sample. So, if it is A, if it is B, new value will be A plus B. Okay. So, sample wise addition, let me draw a better figure, this is got clumsy. So, if it is a sequence like this, say A, B, C dot 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 dot, and I call it x 1 n, and another sequence say A prime, B prime, C prime dot 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 dot, and I call it x 2 n, then y n equal to x 1 n plus x 2 n. This will be, just you have to add sample wise, 0th sample of this fellow, 0th sample of this fellow, they have to be added, that will be new 0th sample. So, this will be A plus A prime, A plus A prime, together you add, you get the new 0 sample at 0th point. Similarly, point number 1 at index 1, B and B prime. So, you add at index 1, there will be a new value B plus B prime. At index 2, again you have got C, C prime. So, you add the two values, you get C plus C prime at index 2, like that. So, at every index, take the sample here, take the sample here, add the two, that will be the new sample at the same index. This is very simple, this is called addition. Then multiplying a sequence say x1n, if you want to multiply by say say beta into x1n, is nothing, every sample will be multiplied by beta. So, 0th sample earlier was A, now it will be beta A, next sample was B, so it will be beta B, next sample was C, now it will be beta C, okay, dot 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 dot. So, scalar multiplication of every sample means multiplying by every sample, that is beta times a sequence means any scalar times a sequence means take every sample multiply by the scalar, each of them multiply by the scalar. Okay. Then comes a very important thing, shifting, delaying. First, what is shifting? Suppose you have been given x of n. Okay, it has got a value at 0th point, maybe A, then B, then C, dot 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 dot. Okay. At -1 it has got say maybe A prime, at -2 it has got say B prime, dot 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 dot. Suppose this is a sequence. If I have y n is equal to x n minus 1, just n minus 1. If n is an integer, n minus x is a function of some integer, right? X 0 has a value, x 1 has a value, x 2 has a value, everywhere given. So, if n is an integer, n minus 1 also is an integer. So, x of that also has a value, from here only I can pick up. So, how will this look like then? So, for that, what is y 1? Suppose as an example you take y 1, y 1 will be x of 1 minus 1 0. So, at index 1, that is why this I am plotting y n. So, at y 1 value will be x 0. So, this fellow will move here. So, it is moving to the right. What is y 2? It will be x 2 minus 1 x 1. So, this was x 1, this will now move here y 2. So, this is moving to the right, this is moving to the right. What will be y 0? Y 0 is x minus 1, that is this guy A prime. So, A prime is also moving from left, so it is shifting. So, this sequence is just shifted to the right by 1, okay, if it is n minus 1. If it is y n is equal to x n minus say k, where k is an integer, how will it look like? Start with y n equal to k, n equal to k means k minus k 0. So, at n equal to k y n, that is y k will be x 0. So, x 0 from here into A, this sample value will move here. So, it is making a jump from 0th index to kth index. So, it is okay. Then y k plus 1. If you put k plus 1, it will be k plus 1 minus k. So, 1. X 1 from location 1 will move to location k plus 1. Okay. Y k plus 2. Y k plus 2 will be x 2. So, this guy C will now move here. So, you see they are jumping from 0th to kth, from 1th to k plus 1th, from 2th to k plus 2th. So, the sequence is shifted to the right by k, if I write x n minus k. Okay. On the other hand, if I have y n is equal to x n plus k, then what will happen? Start at n equal to minus k. Y minus k will be x minus k plus k, that is 0, x of 0. What was x of 0? A. So, this A from here will move here to the left side. So, it is moving to the left. At minus k plus 1, there is further minus, y of minus of k plus 1, if you put here, you get x minus 1. Sorry. Say, come here first, I will go to there later. Minus of k 1 less k minus 1, say. It was minus k, to the right will be 1 less, so minus of k minus 1. Y of minus of k minus 1, if you put that here, at this point you will see it will become x 1. So, this guy B will come here. So, A is moving to the left by k, B is moving to the left by k. So, in fact, that way you can verify every sample is moving to the left by k, that is sequence is shifted to the left, we call it advanced by k. So, if k is negative, sequence will be shifted to the right by k, if k is positive, it will be shifted to the left by k. This shift has something to do with delaying. If it is a real time signal, that is if these sample points correspond to time axis points, then it amounts to delaying or advancing, that I am coming to in the next module. Thank you.